All right, I want to work through some differentiation rules for vector functions. I'm not actually going to do examples of a lot of these. I'll let you work through some in the homework. It shouldn't be too challenging for you, but I do want to explain the rules to you so that you can use them. So first off, if you have a constant vector function, what is that? Maybe a vector function of the form r of t equals 310, or that was not 310, that was 300, 310. Then each component function is constant, and so you can sort of guess that the derivative of the constant vector function is the zero vector, right? You get out a vector in each of these. Okay. Now, what about if you multiply a vector function by a constant? You expect that this should be exactly CR prime, and it is. What about the sum or the difference of two vector functions? You expect that this should be r prime of t plus or minus h prime of t, and it is. Here's where we begin the three different product rules. So the first one is you have a vector function and you're multiplying by a scalar function. Let me show you an example. Maybe you have like t squared times t sine t cosine t. Okay, so this would be the f of t, and here's the r of t. So what do? Well, you could just multiply the t squared, and that's what you'll do practically, but it's good to know these rules. So it turns out you can do the regular product rule. This becomes f prime of t times r of t and then you're going to get plus f of t r prime of t. And I just want you to realize that you can certainly multiply r by f prime, and then you can compute f prime and then multiply that by f, and you get another vector function in the end when you put it all together. Okay, what about the dot product? Well, basically, here's another way to multiply. These are both bona fide vector functions. Taking a dot product is going to give you a scalar, so ultimately we're going to get a scalar out of this, derivative of a scalar. So somehow this is actually just a Calc 1 derivative in some sense. And so what's the formula? Well, the formula is the same old dot product. It's r prime of t dot with h of t plus r of t dot with h prime of t. And so, of course, the dotting puts you back into scalar land. Okay, what about the cross product? Well, this output is going to be a vector function, and so you're taking the derivative of a vector function. You're going to get a vector function. Well, again, it's the same sort of product rule that you've seen before. It's r prime of t cross h of t, and then what we're going to do is we're going to add r of t cross h prime of t, and that's the cross product rule. So a lot of these in practice you'll just compute the cross product and take the derivative, but I want you to know what's true. Finally, there's a classic chain rule where you're plugging in f of t into a vector function. Let me just jot down a quick example and then I'll erase it, but maybe you have like I don't know, r of t is the same. We'll just do t sine t cosine t, and maybe f of t is t squared, and you compose them, and now you have a t squared, sine of t squared, cosine of t squared. And so it's that sort of situation. And it's exactly the same chain rule that you would expect to hold. It's r prime of t, sorry, not r prime of t, that's not what you would expect, r prime of f of t, there we go, times regular times f prime of t. So remember, if I don't write a dot, it's just a regular scalar times a vector. The dot here is actually saying take the dot product. So those are the different differentiation rules, and you'll get to play with those some in the homework. It turns out we can integrate. If I have a vector function that looks like this, then the integral from a to b of that vector function, we're going to do this a lot later in the course, but this is defined as the integral of each component. So this is the integral a to b of the first component, f of t dt, the integral a to b g of t dt, the integral a to b of h of t dt. So it's exactly what you think it should be. You just integrate each component function. So I thought we'd do a quick example, just to do some example. Otherwise, this video is going to be no examples. So we're asked to, here, let's slide this up. We're asked to work out this integral, that is a pi halves, where r is given. And so we can just write it down. So this thing, here's how I would write it. This thing becomes, well, it becomes 2 times the integral from 0 to pi halves cosine of t dt times I like the ijk notation here, and then plus the integral from 0 to pi halves sine of t dt j, and plus, I'll pull the 2 out, 2 times the integral 0 to pi halves of t dt k. All right, so that is the setup, and the point is you can just integrate each one by itself and then put it back in vector form. And so you can work this out for yourself. You integrate cosine, you get sine. The derivative of sine is cosine. Sine of pi halves is 1. Sine of 0 is 0. So we get 2i plus, I'll let you check the next one, is just j, plus you're going to get a pi squared over 4 times k hat. So that is what you get. If you want to put it back in vector in the standard form, you could say 2, 1, and pi squared over 4. All right, so that's an example. Last thing in this video, given a vector function r of t, the unit tangent vector for r of t is, well, what I want you to do is, first off, notation. We're going to use big T for this, so big T of t. And this is exactly, it's good old r prime of t, but then you want to divide out by the length of r prime of t as well. So let's just do a quick example of this. I think I said I was done, but I'm going to squeeze one more example in. Let's do, excuse me, let's do r of t is t, let's do sine t and cosine t. So then we want to find the unit tangent vector t. So first we're going to compute r prime of t, and we're going to get, well, we're going to get 1. We're going to get cosine of t, and we're going to get minus sine of t. And now I want to compute the length of r prime of t, and I'm going to get the square root of, let's see, well, 1 squared is 1 plus cosine squared t plus, it's really minus sine all squared, but the minus goes away, so sine squared t, and we can erase the tail here. All right, and so this just becomes the square root of 2. In this case, sometimes this doesn't simplify, meaning the t's don't cancel out, and you're actually left with t's. That's perfectly fine, perfectly fine. In this case, it canceled out. And so the point is, for this problem, the unit tangent vector t is just the vector 1 over root 2 cosine t over root 2 and minus the sine of t over root 2. And we'll see in 10.8 that, yes, you can certainly have t's when you're dividing by, no problem at all. But in this case, they all canceled out. All right, great job. You finished 10.7, and now you just have to do 10.8, and you're done for the week. Good job.